Hello everyone. So if you have been on Twitter or LinkedIn this week, you have probably seen everyone talking about DeepSeek OCR. The headlines are wild. Like some people are posting it like 10x compression, pictures worth 1,000 words, and unlimited context windows. And honestly, when I saw this for the first time, I thought, okay, DeepSeek has just released another OCR model, and we have seen many other OCR models in past. So what's really new about this? But then I actually read this paper and I realized this is not just about OCR model. This is something much bigger, like using images to compress text. So today what we are going to learn in this video is we will be going through the actual paper together, understand what exactly the problem that they're trying to solve, see how their solution works, and then I'll show you how to actually use this model. So we are using the model which is present on the Hugging Face. So as I'm already started sharing my screen, let's deep dive into the DeepSeek OCR paper that was released um, by their team. So let's dive in. So let me move to the introduction here. So see, so before going to talk about this paper, first we need to understand what exactly the problem is. So here in the very first sentence, if you see what they are mentioning is current large language models face significant computational challenges when processing long textual content due to quadratic scaling with sequence length. So this is bit understandable, but let me explain you this in very simpler terms. So when you use any LLMs like ChatGPT, Grok, or Cloud, or even Gemini, every word becomes one token, right? So if you are using 1,000 words in a prompt or in the query that you are trying to upload, it will be around 100,000 tokens roughly. Like your 100 words is equal to 100 uh, tokens, or 1,000 words is equal to 1,000 tokens. So now here the problem is about the computational cost. So when we say the, let me change it to computational cost. So when we are talking about computational cost here, they are saying that it is not linear, but it is quadratic. So what do we mean by that? Like not linear. See, linear graphs are like this, but quadratic are like this, right? So how do we understand it in in terms of computational cost for tokens? So suppose if you have 1,000 tokens, then it is taking 1 million operations, and for 2,000, it is taking around 4 million, and for 10,000 tokens, now you can guess the number, which is around 100 million operations. So you see, right, how this is exactly exploding as we move or as we grow our tokens further. So this is the reason why our context windows are expensive and limited. And let's move back to the paper. So DeepSeek team asked a very simple question to themselves, like why are we feeding text to vision language models as text? Think about it like if I show you a page from a book, which is consisting of text, which is 1,000 tokens, and as an image, if I give you, it can be 100 vision tokens only. Okay, let me try to explain it here. So suppose if I show you any book to you and say that, okay, you have around, in text, you have around 1,000 tokens, then as an image, it can be only 100 vision tokens, right? So this is like 10x compression that we are seeing here. So you might be thinking, but don't we lose information when we compress an image? That's exactly what this paper test. can you actually compress text into images and still read it back accurately? So that's the whole part of this paper, and uh, which is like really good one. So now let's start looking at the uh, 1 minute. The first image which is present in the paper here. So if you look at this, they have tested this on documents with different amount of text. And at 10x compression, they are getting 97% of accuracy. And at 20% compression, they are still having 60% accuracy. So, which is like really good. Uh, to think yeah, I can zoom in. So now you can see here, right? So this is like really good. But here is what makes this paper more interesting. It's not about the OCR. They are exploring, can we use vision as a compression mechanism for long context in LLMs? Just imagine that you are trying to chat with ChatGPT or Gemini, and after 10 messages, instead of keeping all the text as tokens, the model can take screenshot of the old conversation that you have already exchanged messages and compress it. And now you can potentially have infinite conversation history, which is obviously taking very less tokens. And that's the big idea here. And now let's see how actually they have built this. Okay, so to make this work, they need to build a special vision encoder. And let me show you why. So if you look at this particular picture carefully, yeah, let me just zoom in a bit. Yeah, so this picture, so this is the figure two from the paper, and I love this diagram because it shows the problem with existing approaches. So see these three types of encoders over here that are present. So the first one is they are there is vary, which is dual tower. So what it does is it uses two separate encoders in parallel. And what is problem with that? Really complicated to train and deploy this kind of encoders. And you need two pre-processing pipelines, which is hard to do pipeline parallelism also. And the second one, if you see here, which is tile based, like intern VL. Okay. So if you see here, this is like intern VL series. So what it does is it chops your image into tiny tiles. And what's the problem with this is if your native resolution is very low, like you can think of 448 by 448, a big document gets cut into hundreds of pieces. And what it does is you end up with too many tokens, and which is like so much. And that's the main problem with this. And the third one, if you notice here, it is adaptive resolution. It's like when two. So what it does is it processes the full image at any resolution. And the problem with this particular uh, encoder is it is massively using your memory, and it has like your GPU can literally run out of memory because you will be using high resolution images in it. So this is really good diagram. And now I hope you have got some idea about like what exactly this diagram is talking about, what encoder models and problems that they have mentioned over here. And if we see the figure three over here, this one, right? So this is like the deep encoder uh, solution that they are proposing in the figure three. What they are telling is look at this entire design very carefully. Okay, it is really, really elegant. So let me point you out to the very first uh, stage. Okay, where it takes your input, like it takes your 1024 and 1024 image, and it breaks down all of them into 64 by 64, uh, which is constituting around 4,096 patches. And then what it does is it will use SAM base, and the SAM base is nothing but like 80 million parameters. It has 80 million parameters with that. And then you have a window attention, which is generally used for uh like for each patch. They will only look out for the neighbors. And what it does is this will keep your memory very, very low. This is like entirely about your local attention, local SAM attention, I can say. So, and then what you have next is the compressor. Okay. So, what exactly this compressor is doing over here? So, what it does is you can say that entire magic, right? Like the magic, how it's compressing and all, like that's happening here. So we have a two-layer CNN over here. So what they do is they will compress this with the 16x, if you see here this one, and then whatever the 4,096 tokens that you've got will be compressed to 256. And this happens before global attention that you have. So maybe let me write it over here for you to make you understand. So see, first we will take around, okay, first we will take around 1024 by 1024. Okay, this is the image that we take. And what they do is they will break this into patches, which will be 64 by 64 uh, patches, which will be equal to 4,096. So now this 4,000 will be undergoing in the compressor where they do 16x compression. And whatever the 4,096 is there, this tokens will be reduced to 256 tokens. And this entire thing is happening before our global attention. If you see, before this itself, they are reducing it to 256. And now in the global attention, if we see here, the clip that they have mentioned it as clip, now what it does is it will take those 256 tokens and it uses clip large model, which is like around 300 million parameters. And now it does the full global attention. And all this global attention is going to happen only on 256 tokens, and it's very much manageable. Okay. So now you might be thinking that, okay, what's exactly the brilliance here? If you did global attention on 4,096 tokens, that's around like 16 million operations, right? Which is very huge, huge memory. But when you're trying to compress it first to 256 before you sending it to global attention, and then you are performing your global attention only on this 256, which is only around 65,000 operations. It's like 250 times less than what you would have done on 4,096 tokens. So the philosophy here is cheap operations, like which is window attentions on many tokens, and expensive operations will be only taken on global attention on a very few tokens. Maybe let me write that clearly to you. So if you see here, what exact operation is, cheap operation will be taken on window attention, and where you have many tokens on them, many tokens like 4,096. And then uh, the expensive operations will be taking on 256. 256 tokens, which are like kind of which will be done in the global attention. So this is what uh this is what is happening in this entire paper. And then If we just in your free time, I would encourage you to go through this entire architecture, and they call this architecture as deep encoder. Okay, it's deep in the sense that it is processing the image in a stages, not all at once. Okay, I hope you have uh, got an understanding about this architecture. So let me move to the next page over here. Yeah, so this one. So if we look at this particular image now, which is like this table one, okay. So there is one more thing that we need to understand is they have designed this to work at multiple resolutions. Like now, if you see here, tiny, small, base, large. So tiny is taking around 512 uh, by 512, like which will give us around 64 tokens, and small is around 640 by 640 image, which will be 100 tokens, and base is 1024 by 1024, which will be 256, and then large is around 1280, which will be around 400 tokens. So why they are proposing like these multiple modes? Because they are testing how many tokens do you need for different documents, and a simple slide presentation, like, right, maybe 64 tokens is enough, or a complex research paper with equations will be around will might need around 400 tokens. One model, you have multiple compression levels, and it is very smart, right? Like you can pick anything which is suitable for your convenience. All right. So we have compressed our image into vision tokens. Now we need to decode those back in text. So if you notice the figure three, which was over here, right? So in the figure three, we can also notice that there is a DeepSeek 3B MOE, which is a mixture of experts model over here. So what exactly this decoder is doing? And if you have already following my videos, I have explained mixture of experts model way prior. So you can go back and look at that particular video as well. But I'll try to explain here again what exactly mixture of experts mean. So this is really a great architecture. Okay, so what it does is it will combine multiple submodels called experts. Each expert will handle a specific part of the image data, or like whatever the input data that we have, and the entire model uses a router to decide which experts are best suited for the current task. Like, let me put it over here. So, in the MOE, generally we have two things. One is expert, and other is routers. Okay, so each expert is an independent submodel, and usually a small neural network are focused on processing specific features or patterns in your input data will be present in your experts. And then what does router do is router dynamically selects the most suitable expert based upon the characteristics of the input data that you have. For example, in NLP task, if the input is a sentence about some technology, the router might choose an expert that excels at handling these technical terms. And then comes the dynamic routing. Okay, so what exactly this dynamic routing is? The router uses a gating network generally. Okay, so what it does is it gating network will try to decide which experts to activate. For each input token, the router selects the top k most relevant experts, um, where usually that k is less than the total number of experts itself. And what it does is it will try to avoid the need to activate all experts by saving the computational resources. That's again the best thing. And then we have the expert sharing. So this expert sharing is a good concept, but what it does is to optimize efficiency. MOE allows some experts to share parameters across different tasks or layers. Um, Let me give an example. So you may imagine that you have an online um, a service, okay, like kind of a customer service system that needs to handle different types of customer issues. That might be technical problems or order queries or inquiries, uh, or refund status, something like this. And you wanted to design a mixture of experts here. Okay, so what you do is you're expert. Okay, you need to define what your experts does. You could have three experts for this. Like one is specializing in handling some technical problems, one is expert in um, having the order issues, one is expert in handling the refund status or refund request. And then what router does is whenever a customer question arrives on your dashboard, the router will determine, okay, the category of issue is so and so based upon the context and the intent. And then it will select the corresponding expert to that particular uh, question that was being asked by the user. And the dynamic routing, what it does is if a question involves both order and technical issues, okay, so your two experts need to be present over here. So the router might choose two relevant expert to handle it together. Okay. So this is how MOE actually works. And let me go back here. So I hope you got a good understanding about MOE. So now what exactly they have done is in the next section, if we see over here, this data, right? So they are talking about the data engine. So they have trained on OCR 1.0 data, which is around 70% of uh, training, wherein it constitutes around 30 million PDF pages in approximately 100 languages and 25 million Chinese and English like English PDFs, which are around 5 million other languages. And there are two types of uh, like kind of data that we have used. One is only text and other is fine labels. Okay. And that information is something which will be there here if you see the ground truth image and fine annotations with layouts. So this is how it looks. And if we read furthermore, we have OCR 2.0 data. So which is again 10 million charts which are rendered with matplotlib and pie charts. And then we have 5 million chemical formulas, which are in some format which is friendly with the chemical formulas. And then we have 1 million geometrical diagrams over there. So entirely all these things they have used in their training data. And even if we move further, yeah. So over here and over here, like what we are saying is, right, no, so we are, oh, yeah, yeah, this particular image. If you look at this image right over here, this image, so they don't just do OCR, they can pass chats into HTMLs as well and convert molecular images to smile strings. So general vision, they have used 20%, like which is caption and detection task. And for text uh, based, they have used pure language data. This is diverse mix, and this is why the model is really so capable at doing what it does. So if you just notice here, the table 2, let's talk about this table 2. So the moment of truth is like whatever the training data that they have prepared, even the model, is it really working? So that to answer that particular question, the answer is here in this table. So this table is nothing but the compression study on the Fox benchmark. These are like English documents with 600 to 1300 text tokens. And if you notice this table very carefully, you see 600 to 700 text tokens. They are providing 98.5% accuracy, which is 6.7x compression. Okay. And then 900 to 1000, which is around 96.8 accuracy. And 1200 to 1300, you can see over there, like which is 87.1 accuracy. Okay. And this is around 12.6 compression. And for practical OCR performances, you can look at the table 3, which is Omni Doc Bench. So they have uh, performed like by taking some kind of text data, they have performed the similar test on DeepSeek OCR as well. And in the passing task, like what they have noticed is, if you can also see that there is GPT-4o present over here, and they have also bet GPT-4o on this benchmark. And you can see that DeepSeek OCR is small, and even the base large, everything, every model is like doing really better for the tokens which are present per page. And the qualitative results are also really, really cool. And if you can just look at the next pictures, which are like figure 7. So this is like about deep parsing financial reports and extracting charts from it. So this is exactly what it's doing. And then if you even notice here, this particular one, this particular image, okay, so what it does is they are extracting chemical uh formulas from this, and this is also like super accurate. And so here, yeah, if you notice even this figure 11, they are like supporting approximately around 100 languages. So this is seriously a capable model. And yeah, and now rest of the paper that you can go through by yourself. And it only talks about how exactly DeepSeek is achieving, what else the areas that they have tested on. You can just go through them. But I hope you have understood what exactly is the problem statement and what is the solution, what was the architecture that they have proposed over here. And then in the